I am a fan of all black modules. So this is what they're called. They're called all black. So, over on the right is what most solar panels look like. An aluminum frame, these little cells that you can see. An all black module takes this white back sheet behind the cells and makes it black instead. So you still have the cells, but you can't see the edges of them. And then this metal frame is anodized black. And that costs a little bit more money too, but the manufacturer does it. So at the end of the day, customers prefer all black modules because they, frankly, look better. And so some manufacturers like Canadian Solar say, look, all of our residential modules, which are slightly smaller in frame than the utility scale modules, you can use utility scale modules at residential sites and vice versa. But a larger panel just makes better use of your racking system. It just gets too large to handle on a rooftop safely. And so you use a 60 cell module for residential, a 72 cell module for utility scale. When I select my 60 cell silicon module for residential, I'm looking for an all black module. I don't really care who it comes from, but I want that aesthetic look so that it looks better. Aesthetics are back on that property value idea. An ugly solar array is not going to retain its value. If it doesn't have curb appeal, if the customer drives up curbside, looks up at the roof and sees a solar array, they think, that's a home I want to buy. They don't know anything about how much energy this solar array generates, or what the electric bill of this home is, or even what the price of electricity is in their area. A new home buyer, it's more, A, can they afford it, and then B, do they like it? And that solar array sends a message of, this is a home with low electric bills, it's a green home. It might be the most horribly inefficient home on the block, and the previous owner decided to, not even consider efficiency and overkill it with a solar array. Or it could be a 1 kilowatt solar array that only generates, 10% of the building's electricity. Either way, that curb appeal determines how, if the customer is gonna spend more money on it. And so aesthetics are important. Even a rooftop like this, it's like, okay, this is the backyard, and here's the solar array, and you can't really see the roof from the yard. But if you walk 100 feet away from the house and turn around, you can see the roof. Most rooftop surfaces are visible, even if they're not street facing. And the fact is, we can tell from this design that the designer did not pick up on this roof penetration here until they got out to do the install, and they said, oh, what was supposed to be right here is now over here because there's a vent in the way. And the fact is, there are products on the market that'll let you replumb vents on the rooftop that could make this array workable, where the module would fit right there, and they would just plumb the vent out the bottom side of the array, or out of the top of the array. And so that's where a designer can get in and better promote. The solar installer isn't thinking about real estate value, long-term value, down the road value. They might say that, but they're thinking about the cell. Maybe a building designer is more respectful of designing a well-looking solar array that will not appear obsolete down the road because of its aesthetics. So a solar panel is for residential type solar panels are typically 3 1/3 feet by 5 1/3 feet. Utility scale panels are 3 1/3 feet by 6 1/3 feet. The solar panel, the residential type, and unless I say otherwise, assume that I'm talking about a 60 cell residential type panel. The 72 cell panels are actually a little bit more expensive per watt than the 60 cell panels in my experience. You know, the utility scale modules, they're making up that slight cost difference in terms of racking and labor and wiring efficiency. So there's not much per watt difference in price between 60 cell or 72 cell. If you do enough supply chain management and you're patient, you can find all black modules for the same price as regular modules. The solar panel industry is a mature industry. There's UL listings for hail tests. Most modules are rated for 1-inch hail at 50 miles an hour. Some modules have stronger glass and stronger frames and go all the way up to, you know, something like 75 miles an hour. And so, you know, when I have a solar array on my rooftop and I get light hailstones, you know, what I think is, oh, that solar array is protecting my roof. It's not destroying it. Now, if the solar array only covers half my roof, then I don't know what good is the protection. But most solar is putting a hard shell on the top of your house. And not only that, that's good for the shingles underneath too, because shingles primarily degrade because of direct exposure to sunlight. You put them in the shade, assuming they're well ventilated, protected from debris, they're gonna last longer. Now at $250 to $350 a watt as your installation price, we can calculate a number that is rarely calculated by the solar installer, where if we know that a typical 60-cell solar panel might be 300 watts, and we know it's 3 1/3 feet by 5 1/3 feet, we can take the dollar per watt cost of the panel, multiply by how many watts to get the price of the panel itself, divide by the dimensions, and get a dollar per square foot number. And so for solar per square foot is really expensive. And a lot of installers never think about the price per solar per square foot. But if you're in building design, you look at $40 to $60 per square feet, and you're like, yeah, that's a lot more expensive than a roof. And the answer is yeah. You know, you want to get into solar because it's expensive. You know, solar thermal is twice as efficient as solar electric. If you have a huge need for hot water, like you're a public swimming pool or a hotel with a swimming pool or a prison system with tons of showers, and you have tremendous needs for hot water, or if you're an experimental building designer and you want to have the solar thermal system do some air conditioning like a radiator on your car, or heating your home through inlaid floor radiant heating, you know, there are cases where solar thermal can outperform solar electric. But say at the residential scale, you know, which do you want to do? Would you rather do a $20 or $30 or $40,000 residential solar project, or a $6,000 solar thermal project? A $40,000 solar array can take out the entire electric bill. The $6,000 solar thermal array can only take out the water heating bill. And so there are some merits to the fact that solar can do everything, that your rooftop is, you know, kind of an out of sight, out of mind surface, that you get a high dollar value that attracts a higher rate of professionalism into the industry. Solar panels have 25-year warranties, and the kind of panels that I like, you know, I'm very manufacturer agnostic. I will install bankrupted solar panels if we have to. You know, when I'm doing an off-grid project, every single dollar we have on the project is going into that battery bank. We have to use the cheapest modules we can. I don't think that module manufacturers are going to stick around. You know, more solar module manufacturers will go out of business that are in business today than that will stay in business. And maybe the highest quality goes out of business because their costs are too high, or the lowest quality goes out of business because they stink. You know, so the guys at the top and the guys at the bottom can all go out of business. So who's gonna stay in business? Who knows? It's a complete luck of the draw. You know, you just try and swim with the biggest fishes, but at that point you also have to consider cost. You know, if I can buy a solar module that doesn't have a warranty for 50% less because it's unfinanceable on a big project, that might be what it takes to do solar in a market like Oklahoma, where you have extremely cheap electricity. But anyway, when I pick out a solar module, the number one thing I look at is the warranty, because as we'll see in maybe the next slide, but we'll see in a little bit later, you can find a warranty that looks like a stair step, where it's 90% of the power rating for years 1 through 10, and then 80% of the power rating for years 10 through 25. Or you can find a warranty, it's actually a logarithmic curve, but it's so straight that it looks like a straight line. So for the mathematicians in the room, it's a logarithmic warranty, but for the layman in the room, instead of being a stair-step warranty, they call it a linear warranty, where it's actually every year decreasing power level. And that means, you know, the manufacturer only needs to be in business for another year or two for you to determine if there's anything wrong in terms of the workmanship quality, and so you can get the module serviced in that year. When we talk about degradation of a module, it degrades over time, there's a few factors that come into play. You know, the first is a one-time loss over the first few months of the system. And what this loss is, it's called light-induced degradation. Imagine the solar module, the solar cell itself is a billiard table. And there's pockets in the billiard table, except now instead of the pockets being in just specific places, it's really the pockets are all up on the top of the cell. And the electrons that are organized in the cell are hit by photons in the sun. They come out of where they're supposed to be in the cell and start careening around the silicon in the cell. Kind of like how electrons flow through a copper wire. So, you know, copper's solid, but electrons can flow through it. Silicon is solid, but electrons can flow through it when they're activated by collisions with the energy particles in sunlight. So after these electrons start going out whichever direction they want into, and then they eventually come out the top of the module and go back in the bottom and fall back in to where they're supposed to be, over time, these electrons start to etch little pathways into the cell. And when the electron that's trying to go one way hits this pathway, it gets wobbly. It's almost like an old billiard table where the cue balls have etched little pathways into the felt. The same thing happens over the first period of use of a solar array. Another analogy would be a car engine that's never been run before. After it runs a few times, it has a little bit of gunk inside it. You know, the miles per gallon rating dips down a little bit. You see this one-off degradation in the first few months of the array. And so that degradation might be 1.5%, and a stair-step warranty would be often for 97%. Whereas, a linear warranty would be at 97%, whereas a stair-step warranty at that time would be 90%. And generally, modules degrade at about 0.5% a year. So common to module the lifetime of the array to be 30 years, 25 years is the performance warranty. What we see is the stair-step warranty is way too conservative. I mean, the problem with a stair-step warranty is if this module degrades out of the box, it degrades by 7%, and then the degradation levels off, you might never get to your warranty until year 18 or 19, even though you're producing far less power than what you expected because of some kind of defect. These defects almost never become an issue. System owners make a mistake by focusing too much on module quality and not focusing on quality throughout the rest of the project. The very first place I cut budget, if I need to cut budget, is module quality. You know, I'll dive into the bargain bin and run from the top shelf, but I won't have that same attitude with any other system component. You know, the inverter absolutely has to be high quality. The inverter is the workhorse of the system. But anyway, what's nice about a linear warranty is it more closely mimics the natural decay of the module, so that if something goes horribly wrong, you can trigger the warranty as soon as it occurs. Now, I got to tell you, most modules have 3 bypass circuits in them. And so what happens with a faulty module is usually something goes wrong in one of those circuits and it then gets bypassed. So normally with a faulty module, the production drops down to about 2/3 of what it is, and that's a warranty, well within the warranty range, and it's very easy to diagnose. It's more for what we saw in previous slides, those micro cracks over time can degrade the module performance, and it's really unsettled on what causes micro cracks. Is it the installer flexing the modules, or is it an issue with the silicon purity? You know, it's not just a install or manufacturer issue. But the point is, if you're a client and your module has all these micro cracks in it and it's not performing what you want it to perform, you know, it doesn't matter who supplies the module. You know, whatever the issue is, you're going to pick up on it over the first few years of the array. And so you need a warranty that'll allow you to address the issue over the first few years of array ownership. You know, down the road is anybody's guess. But what you need is to, if you discover a problem with the array in the first few years of system ownership, you know, you definitely want the warranty to be protecting you. Now, most solar installers will tell you you're never going to have a problem with your system. Most experienced solar installers will tell you about 1/3 of the customers have problems with their system. So there is truth to the fact that solar is low maintenance. Often you never have a problem, but when you do have a problem, you got to do something about it. And solar is not bulletproof. So we're going to talk about maintenance issues more, but how I buy a solar panel, you know, just to give you an example, I recently bought these for my residential project. I found some Jinko solar panels, and Jinko is a large, you know, tier top volume Chinese solar module manufacturer, and we got these panels for 50 cents per watt. And that was just a week ago. Module prices are starting to spike because of fear over the import tariff, but we were able to still get modules at a good price simply through rolling up our sleeves and doing some supply chain management. Now, here's the thing. When you go online, you're going to find dozens of online solar material distributors. And yeah, you know, I have favorites, but your favorites can be different than mine. You know, there is some advantage to having a more personable relationship with whoever you buy your material from, but also you do a little bit of competitive pricing. Now, when you go to the website of the company, you might be researching module pricing and say 95 cents per watt, 93 cents per watt, and you're saying, well, JR, you just bought panels for 50 cents a watt, and you know, you're telling us in your industry data that solar module pricing should be closer to 60 cents a watt. So how do I buy modules down here and not pay, you know, a little bit of a markup from the distributor? And the answer is, you know, supply chain management. You roll up your sleeves, you contact multiple distributors, put the project out for bid. You have to be a little bit organized to do that. But the best way to research it is you may go to the website and they say, okay, sign up to become a dealer. And to be a dealer, you have to be a licensed and insured contractor sometimes. You have to be a master electrician sometimes. Sometimes they don't care. They just want you to fill out the form and you're a dealer. It's not it's not nearly as closed. I'd say it's more like the opposite of, say, Carrier HVAC units. They're a big brand name air conditioning company. And to be a Carrier HVAC installer, you have to be an HVAC contractor for so many years, and there's an exclusive geographic distribution territory, and only so many other contractors in your area can be certified for that system, and you have to buy the air conditioner from the contractor. It's a tightly controlled supply chain. Most solar is not a tightly controlled supply chain. Most online distributors have a newsletter form on their website. You just go to their website, sign up for the newsletter. Once a month, you start getting offers, and so that way you can get pricing the same as me, actually. The module that I got 50 cents a watt from, the hard part about this retrofit is we needed to find a solar module that was similar to a module made 2 or 3 years ago in terms of exact form factor, so that it matched the older array on the rooftop. And those modules that are older have a lower price. I love buying last year's solar panel because you can shave more than a year off of your payback that way. But if you're looking for a 3 or 4 year old solar panel, sometimes they go up in price because they're harder to find. Anyway, the supplier we ended up buying from, on their website, it's very clear. They say, we do not sell to residential do-it-yourselfers. For that, we have a residential vendor. Here's their link. Go through them for residential material. And yet, even so, we were able to call them up, and even without having a vendor account, order less than a pallet of solar panels and racking material and microinverters at the same price as many other contractors who already have a relationship with them do. And the reason was we were able to give them a design document. Starting out with, hey, I have this material list. Do you wanna bid it for me? Rather than, I have this rooftop, can you do a solar project for me? They just looked at that as saying, okay, JR, we've never talked to you before. We don't know anything about your business, but you're an engineer and you have a material list of solar that we can supply and is in our inventory. So, they were able to get the quote to me in a matter of a day, and we got the material ordered, no problem, for this residential do-it-yourself, overcoming that barrier, specifically because you can. These solar vendors, they don't know who is going to be buying solar 2 or 3 years from now. Maybe residential tanks and it's all utility scale. Maybe utility tanks and it's all commercial. And so they're looking to expand their Rolodex as much as possible. And so there's still definitely, you have the ability as a design architect, as a design engineer, to contact with confidence these larger material distributors with contractor programs and contractor pricing. And it's really not that. It's just that if they have a closed wall contractor purchasing system, mainly they're just expecting you to do most of the design work yourself and just call them with material orders already to go. Now, in terms of module selection, the solar panel is the most reliable part of the system. We use solar on the International Space Station because solar is reliable. I have to go outside my house and get up on the rooftop. That's really annoying. If I have to go into outer space to fix my solar panel, that's very costly. The panel is very reliable. When you have failures in your system, it's uniformly not the panel's fault. I've only replaced 2 solar panels in my 8-year career that were because of module defects. And actually, the more I learn about it, the more I think the install crew, it was a ground mount array, and 2 panels didn't work after the install. And what I remember is the day 2 after the module started going up, you have these kind of post mount systems, and the panels go up. And then on day 2, I got to the end of I got out to the job site in the morning, and I saw little butt prints going down the row of solar panels, because once the first row went up, this crew started the second row, and then we got people sitting on the panel. The pressure rating of the panel is very high. And so they're rated for 90-mile-an-hour winds all the way up to, you can find some panel ratings for 120-mile-an-hour winds, some that can even do more than that. Usually at that point, you're just looking for a racking system that can hold everything together in a hurricane. But the problem was, if you apply a point load to a panel, such as in a tornado, a giant tree branch comes and smashes the front of the module. A forklift operator is getting way too confident in the ability to slam and solar panels all over the job site, and that they shake the panels pallet a little too much. Or you're putting a solar panel on a racking system, and you've propped it up against the ground mount rack, kind of doing some staging, and then a big gust of wind comes and blows the module over, and it smacks on the ground flat all at once. Those kinds of extreme impacts can shatter the glass. This is basically the same as your automobile glass. A rock can hit it, but if it's too large, it can, too much momentum at one point, it can shatter. In terms of actual module defects, these 3 panels over here are different than the one on the right. This was caused by extreme weather with a large tree trunk, hitting the panel. These are called micro cracks, and they occur because in a polycrystalline cell, you get these grain boundaries in the silicon, and these grain boundaries, if fractured, if stressed by someone sitting or kneeling or elbowing on top of a solar panel, or walking on them, because if you're, I would not walk on a solar panel, but like 120 pounds or less, you can just walk across the array, not see any damage, but you might be causing a little stresses in the solar cell itself, and then the electricity starts arcing across it. Either the crack gets so large it can't conduct current. It's not always uniform. Sometimes these micro cracks don't impact performance at all. Sometimes they impact performance completely. So here's a micro crack. I started learning about micro cracks, and I thought, uh-oh, I need to go look at my solar arrays and see if this is happening on my solar arrays. And even though the production on these solar arrays is good, I get out to the field, and this is one of my micro cracks that I found. So it's a universal issue. It's not just a polysilicon issue. Instead of thin film micro cracks, where you have a more uniform cell from the top to bottom, and so we can see a little bit more uniformity and symmetry in this crack. And then what it comes down to is, even though, say, monosilicon is not immune to micro cracks, monosilicon, this little cell right here on the right, is formed by slicing a bar, a column of pure silicon. It's not a casting process, it's different, but without getting too much into the detail, this is like you have a crystal of silicon that's, a big salami shape, and you just cut the pepperonis off the end, and this is how monocrystalline lays out. So it's a uniform crystalline cell. You don't have these little microscopic grain boundaries. Polysilicon is not made from a bar, it's made from a sheet. and so these cells are more likely to microcrack. And for that reason, what my preferred solar module is, and this is really splitting hairs because a lot of modules are more similar to each other than further apart. But my preference for residential in particular is all black monosilicon in terms of quality. You know, where it comes from, I don't really care because it's a crapshoot. But if all else is the same and I have my prices are in and they're all clumped together really close, I'm going to go with the all black monocrystalline 10 times out of 10. And from that point, you know, you go to your distributor, you pick out which module you want to buy, you pull up the spec sheet, and then solar design is essentially how many rectangles can I fit onto this larger polygon. You know, it's not that difficult of an exercise to do an array layout. So you start by sketching your rooftop, and for this, I'll commonly just use Google Earth. You know, Google Earth has a ruler tool on it, and there's two things you get with, or three things you get with Google Earth. One, you get distance, so you can measure out rooftop dimensions. Two, you get headings, so you can actually measure out shadow lengths and get the heading of that shadow. And then you can find, the third thing is you can find the date that this picture was taken. So if I have the date that the picture was taken and I have the length of the shadow, I can go and use a sun angle chart to find where the sun was when it's casting a shadow of that bearing on that date. And therefore, I can use trigonometry to calculate the height of this building, the height of this tree. And these are all rough estimates, but you know, if you're doing a remote solar design, you need to have rough estimates because you're not on site. You know, you need larger margins of error rather than smaller margins of error to perform remote site assessment using pencil and paper, you know, not using paid commercial software. But it's absolutely possible to. Now, the one thing to be aware of is that not in National Electric Code, but in International Residential Building Code. So your building, you may be getting an electrical permit, an electrical inspection. You may not have a building inspector come out and inspect your site. That doesn't necessarily mean you can ignore building code. Where the building code comes from is a concern over fire safety. When a building is on fire, it's common for the firemen to get up on the roof and cut a hole in the roof and ventilate smoke out of the building. There are other ways to ventilate smoke out of a building. You could design a building that has a forced ventilation air system, and that would be just as effective, assuming it has some emergency power supply. You may have a fire department, such as the entire state of New Jersey, that says under no circumstance are firemen getting up on top of the roof of a burning building, so we don't care about what happens on the roof because we're not going up there. But in most jurisdictions, even if your electrical inspector does not know about this, there are fire access requirements. Now, the way I remember it is you go 3 feet off the top and 3 feet off the sides. And if you have that clearance requirement, you're going to stay in the good graces of your residential layout. So staying 3 feet off the top and 3 feet off the sides. You don't have to stay 3 feet off the bottom. And maybe you're in a jurisdiction that says, well, you know, if the roof is, if you have an uncovered roof that is street accessible, then on the back of your house you can cover the whole roof. I don't really like that design idea because I like covering the entire rooftop with solar and not just, you know, one surface. You know, if this other side of the rooftop is a good surface, I want to at least vet it for a potential site. You stay 3 feet off the top, 3 feet off the sides, you're going to be in the clear. There's a little bit more flexibility here if you have a gable roof or a hip roof instead of a gable roof, so you don't have a sharp edge here. but instead it's you know, less than a 90-degree turn or something. Anyway, if you have a hip roof, you only need to do 3 feet off one side as long as that roof surface is accessible. So there's a little bit more fine lines to this. But essentially what I'm doing is staying 3 feet off the top, 3 feet off the sides, and then I like staying 3 feet off the bottom too, for a few reasons, but the main one is accessibility. You know, if something goes wrong with this solar module and I have to access it, either, you know, I'm up on top of a ladder trying to access this module, which is not preferable, or I'm up on the other side of the roof and then I have to remove this module before I can service that module. And you know what that means is there's little clips that hold the panels in place. And so what that means is that I'm up here, you know, on my on my knees, kind of Spider-Manning over the solar array with my tools, trying to get my clips. And I'm a giant in that sketch. You know, these are 5 feet long. So you're actually, to get these clips that are at the edges, you really are dangling over the array. And, you know, it's hard because you don't want to stress the array. You're upside down. You're on a slanted surface that's elevated. You're wearing full protection gear. You know, maintenance of solar is not fun when you have to do it. And so I like you know, 3 feet all around just for accessibility purposes, but you don't need to. And if it comes between doing a larger project or a smaller project, you know, a little bit more labor cost in a larger project is never a bad thing from an installer perspective. So you sketch out the rooftop. You mark 3 feet off the sides, 3 feet off the top. In this case, I also did 3 feet off the bottom. There are commercial restraints as well, and I've included the link. You know, a lot of these guidance comes out of California. They're kind of the pioneers of the U.S. solar industry. And the commercial code is essentially 6 feet off the sides instead of 3 feet. And then every 150 feet, you need a walkway. And then lastly, you can't box in your roof-mounted equipment. You know, you need a 4-foot perimeter, and there's, you know, the walkways have to be 8 feet. You know, there's some flexibility in there that you're going to want to read into if you're doing commercial solar design in this report. But if you have a residential type roof, there's no requirements to stay 4 feet off of roof-mounted equipment. It still might not be a bad idea, but you have to stay away from roof-mounted equipment on commercial. So you get your module dimension. There's you have to adjust for the dimension of the clips that hold the module in place. But other than that, solar design is as simple as sketching out your usable roof area and then determining how many modules you can fit. Here's a racking design software that's made from your racking manufacturer, and you can see this was what our array layout looked like, and what we've done is built the array layout in the racking design software. And what it does is it'll generate a material list for us. Now, how this racking stuff works, a solar panel has a metal frame that gets laid across these rails. Now, the module itself is clamped down onto the rail. You have this is called a mid clip, and this little notch goes between two solar panels. And so your solar panel, you know, it goes across the rail here. And then this rail has a channel in it that this little T-bolt sits into, and then you give it a 90-degree turn and it can't come out of the channel. And so you let me see if I can change my color here. You take a clip and you clip the sides of the panel. So there's going to be a little 1/4 inch gap if we use this clip to attach the panels between each panel. And sometimes that little gap length can be problematic because some systems, 1/4 inch is pretty standard. Sometimes it's 1/3 of an inch, particularly on utility ground mount projects. The clips have to be a little bit more robust. or some German, extremely robust, straightforward clamps have a 1-inch gap, which takes up a little bit more space, but also has some ventilation strength to it. So like American would be, I don't care about efficiency, I want more panels on my rooftop, whereas maybe in a higher priced electric market or something, I don't know, I like the American system better. And then at the end, you have a clamp just for the last module. Some other things to note about with this picture is that the attachment points to the rooftop are flashed, and they're all flashed. So that's a good way to see if an installer knows what they're doing, is if they're flashing their attachments. Most installers do at this point. And then lastly, what we're seeing with these L feet here is that they're staggered. So this is a 4-foot on-center L foot, and then on the next row up, we're staggering. What's happening here is that we have rafters underneath the roof deck. But what we're doing by staggering the L feet, we have 2 rails per row of module and attachments 4 feet on center with each rail. And that way we're hitting every single rafter as we go across the rooftop, going with an even load distribution. Now, some rail is rated for a 6-foot span, but if you use a 6-foot span, you have fewer attachment points, and you might think, well, fewer attachment points are great because fewer attachment points means the roof is not going to leak. But the problem is that you got force on your racking system. Your racking system is designed for your wind speed, it's designed for your snow load, it's designed for the exposure category of your system. This is a manufacturer-provided racking sizing tool. Manufacturers want to make it as easy as possible for you to design a system using their product. So every manufacturer has sizing software for racking, for wiring with inverters on their website that you can download and use. And so we put our racking layout into the racking design software, and it spits out that material list of every single item of material that we need associated with the racking system. How to attach the modules to the rail, how to attach the rail to the rooftop. And they'll even sell you bolts and fasteners too, although it's usually much more cost effective just to source that stuff locally from your supply store. Solar rail is very generic from one rail company to the next. Generally, and I think we talk about this a little bit later, but I'm going to pick my racking company not based on their product. It's very generic from company A to company B, but I'm going to base it on how much engineering data they provide me. Back on the fewer attachment points, the fewer attachment points you have on the rooftop, first off, you might get into a situation where you skip over a rafter and you don't have load on one rafter. So you have uneven load distribution across your rooftop, which weakens the roof. But on top of that, the fewer attachment points you have, now it's the same force on the array, the same wind force, but now your point loads are much larger because you have fewer attachments. And so what causes the leak? The fact that you're poking a hole in the rooftop, well, every couple of feet on these shingles, there's a nail that's going through the roof. So is a leak caused because you poked a hole in the roof? No, it's caused because over time that flashing and that mastic deteriorates because of this little attachment point wiggling back and forth. So I like using, I'm not afraid of using multiple attachments. I usually overkill the attachments. Once you do your array layout and you calculate your racking, you also need to figure out what inverter you have. We're going to get into that in a minute. Inverters are getting more functional. You have utility scale battery inverters. You also have inverters that will output power when the grid is down. So this SMA inverter, it's not a battery inverter. You can't wire a battery bank up to it, but you can put in a dedicated outlet so that during an emergency, you have a separately derived power source that you can use during the day. Now, this SMA inverter is much more expensive than a traditional inverter because of that feature. Amongst other things, SMA is regarded as a quality leader. But after you pick out your inverter, the last step is kind of deciding which modules from your layout go on which circuit. Now, I use solar design software to help me. It becomes, okay, if you know how many modules are on each circuit, and you know how many circuits, and you know the inverter can take that many circuits, then the next question is, well, how do you determine which modules are on which circuits? You know, you might get a constraint. Like this was a micro inverter array, so we could have circuits of different lengths, and that meant, you know, if we have this many modules, we might do one circuit here and then go into the roof and build a jumper cable and go into this circuit here. But since that would give us one big circuit and one small circuit, you know, instead we might tie these two circuits together and then this circuit together. And, you know, there's a number of ways you can do this. You know, when you do kind of snakes in a basket, you're kind of looping the circuit through the array and minimizing the number of splices and penetrations. An alternate to consider is, you know, saying to heck with it, our installer is going to build a bunch of jumpers and terminations, and our circuits are going to be just nice and straight and uniform, so that when it comes time to perform maintenance, you get up underneath the array, you see nice organized circuits, and you know what wire is leading where. Of course, you should have circuit labels for that. So let's talk about inverter selection for a minute. You have a few options in the solar industry today. You have microinverters, where you're putting an inverter behind every single panel on the rooftop. You have DC optimizers, which are very similar to microinverters, where you're putting a box behind every panel or every other panel before you wire up to one inverter. Or you have a system where you don't have any of these boxes up on the rooftop and you just have an inverter for the entire system. That's called a string inverter. The DC circuit, instead of being called a branch circuit like AC circuits, you have AC branch circuits in your wall that your power outlets come out of. On the DC side of things, the industry jargon is stringed. And so your circuit sizing is called string sizing. Your solar inverters are called string inverters, as opposed to microinverters that are on the panel level. Your home, the electric grid is all on AC electricity. Your inverter is what converts it, the DC into AC. Batteries are on DC electricity. Your home is on AC electricity. Your cell phone charger is an inverter. You know, the only thing that's special about these inverters are that they're not AC to DC coming out of the grid. They're designed to push to the grid. So they're not draining the grid, they're charging the grid. And that means they have to monitor the grid. But again, an inverter is not a new device. Now, how do you choose which system to use? Well, basically, microinverters are the most expensive, and they're also the easiest. The middle ground that most solar installers in the United States use, the market leader for rooftop solar at the residential and small commercial level, are DC optimizers. And then once you get into larger projects, or you're going for installers that are pursuing the lowest cost in any way, shape, or form possible, there's a newer technology, which is a string inverter with smart combiners. And we're going to talk about that in a minute. But you look at the price difference between, say, the most expensive option and the least expensive option, and you might be looking at a year of payback And the problem with a year of payback is that when you're already talking about a 12-year payback, you start to you lose customers when you go to 13. You lose even more when you go to 14. You have no customers when you go to 15. So, you may be if you're in a high-priced electricity market with a very valuable generation rate, the microinverter versus string inverter price difference may not make any difference. If you are a self-installer and you don't have a lot of experience, you're not going to find a more plug-and-play system than the microinverter. So, you save the money on labor. My preference is for string inverters and smart combiners, and the reason is you have to kind of understand why these microinverters and DC optimizers came to market. They're being used differently now than they were a few years ago. Installers don't necessarily understand that because the technology has changed. It used to be that with string inverters, the tiniest amount of shade on an array would wreak havoc on solar production. And so microinverters came to market to say, well, let's move the inverter up onto the rooftop and put an inverter behind every single module. If you have one inverter for the entire system, it's one system. If you have one inverter per module, it's like you have dozens of independent solar arrays up on your rooftop. And the problem with the string inverters is not necessarily one of parallel versus series wiring. And series wiring, you're wiring from positive to negative and positive to negative, and voltage is adding up while amperage remains flat. In parallel wiring, where you have like your electric service panel, where everything is wired, in parallel to each other, voltage remains the same and amperage stacks up. And so if you just look at it as a voltage and amperage problem, the cloud passes over the array, and if this is a 3-circuit array, the shaded module impacts just the circuit. In fact, there's a bypass for a shaded module that can take that module out of the circuit. But that's not the problem. The problem is when you have multiple circuits coming back into the inverter with multiple groups of modules, the inverter itself is trying to track the best power output of the system based on both voltage and amperage. And if that voltage and amperage being fed to the inverter is jumping up and down, because the cloud is passing over the array, and so now the different circuits are just spiking up and down, the inverter gets confused, and it doesn't operate as efficiently as it used to. So it's not necessarily that one shaded panel is ruining the panels of the entire system. It's that the inverters did not have the technology to individually track the individual circuits. And so microinverters came to market to overcome the limitations that shade put on a solar array. With string inverters, you had to avoid shade like the Black Plague. The tiniest amount of shade would wreak havoc, and so you'd have to do a very robust site analysis. You'd send someone to site, they'd get up on the rooftop, they'd walk the roof, put a couple hours into a proposal and give it to the client. Maybe you win it, maybe you don't. Maybe you get to site and realize the sales rep messed up the design, and now you have to negotiate a contract change with the client and buy a different inverter, and it becomes a real mess if you have field design changes with string inverters. With microinverters, it's more like, that little bit of morning shade that's on a single module because of a chimney, no problem, it's going to be gone in an hour, and meanwhile the rest of the array remains up online. So microinverters came to market to accommodate, to open up the rooftop, to allow you to install into partially shaded regions. The problem with microinverters is twofold. You know, the first is it's more expensive to buy a lot of a little item than just one big item that represents the whole of these small parts. So, you know, these connectors that you're unnecessarily purchasing, the mounting brackets that you're unnecessarily purchasing, the shell of the inverter, all these pieces contain redundant parts, and that drives up the cost. And so the microinverter is the most expensive item. The reason why the DC optimizer system is so popular is twofold. The first is often you're putting one optimizer on every 2 modules. So it's almost like instead of having one solar panel, now your solar panel is effectively just twice as large. No big deal. It's a cost-effective compromise. You don't necessarily need this specific amount of tracking on an array. So that the DC optimizer, you're buying half of the boxes, and then you still eliminate some redundancy by having one inverter. And so whereas the microinverters are doing a DC to DC inversion, DC to AC full inversion process, the DC optimizers are just fixing the output voltage at a constant amount. They're a voltage regulator that feeds the inverter a constant voltage. So the voltage remains fixed even with the strings jumping up and down in terms of amperage, and that allows the inverter to do better tracking. So then we're left with string inverters. And they say, okay, well, we're not going to do module level stuff at all, but we are going to track the input circuits differently from each other, which improves the performance on those partly cloudy days. Now, you know, if you have a roof line that's casting a shadow over the entire string or circuit, you know, that'll take the circuit out, but you don't have that voltage flickering issue that you used to have that would confuse the inverter. So string inverters now, if you have what's called a multiple power point tracking, can provide similar shade advantages to DC optimizers and microinverters. And keep in mind, when we're talking about shade on a solar array, we're only talking about shadows that might be there in the morning or the evening, but that's about it. You know, you don't want to put solar on a shaded roof surface. Shadows get very long in the morning or evening. It's impossible to fully avoid shade. But now string inverters, the top shelf string inverters can do multiple power point tracking. But we also have reasons to buy microinverters now that have nothing to do with their field performance and everything to do with fire safety. The problem with string inverters is that the solar panel is always on during the day. So, you know, imagine a light switch where there's no switch on the wall. It's just the light bulb turns on when the sun comes up, the light bulb turns off when the sun comes down. Well, that means that the circuit that leaves the array and goes back to the string inverter. So the array might be on your rooftop, the string inverter might be on the side of the wall. That circuit has live voltage in it. And if for whatever reason, it may be the solar array's fault, it may not be, but for whatever reason, if the building catches on fire, it could be the solar array's fault. I mean, it's a power system. To say the solar array won't catch the building on fire, you know, you never say never. You have to identify potential safety hazards. Well, the power company shows up, and the first thing they do is turn off power to the building because they want to go into the building and fight the fire. But they're concerned that if they don't know where these home run conductors are, you know, they don't want to swing an axe through a wall and strike a live wire. So recent changes to National Electric Code from 2014 on, and actually 2017 is a little more strict, and this is the 2017 requirements. It's a 1 foot perimeter where any conductors outside this 1 foot perimeter have to de-energize during an emergency. I didn't say during a power outage. You know, you might have a transfer switch and a battery bank, and so when the grid goes out, You know, your array remains on. But during an emergency, the fire department has to be able to show up and through a switch or a button be able to, you know, not only kill the power to the home, but if you have a backup power system, you know, kill power to the backup system, and that has to de-energize the conductor between the array and the inverter. So the way that you do that is now the pass-through box that would transition between the exterior wiring and the interior wiring through the roof. You know, many solar installers will stay outside the rooftop. I think that that is terrible for system aesthetics, although I understand why from the installer's perspective they'd want to stay outside the rooftop. You know, as far as if I'm a general contractor, I'm going to say, good, solar installers, don't go into the rooftop. Keep installing ugly solar arrays because, you know, I like doing internal wire runs, and that's expertise that you don't have. You know, all we're talking about is drilling a hole through the roof deck and putting in a pipe boot with some flashing, and there's even specialized solar specific parts to help you with that. And you know, I'll locate these boxes underneath the array, which is allowed per National Electric Code, and completely hide the entrance point into the building, and that achieves in effect like a wall-mounted television that is just hanging above the wall, but you can't see any of the wiring or support brackets behind it. You know, it's possible to make the array look really good. And now these transition boxes have electronics in them, where it used to be that you just have a positive and negative and ground coming out the boxes, but now they take the a neutral wire between the inverter and the box on the roof. Now, neutral wires in the AC side are used to balance your electricity, but they're also used for communication. And what will happen is when the emergency shutdown is triggered, a communication signal is sent up to the rooftop to tell the combiner box to open up the circuits on the roof. Now, these rapid shutdown compliant combiner boxes have only been on the market for about 1.5 years or so. And so I've been, you know, looking at them, but, you know, not wanting to make any clients a guinea pig. But now that batteries are coming in force, batteries are pretty easy to integrate with string inverters. They're more complicated with microinverters and DC optimizers. And to be quite honest, you know, what I'm tired of is, you know, these microinverters and the DC optimizers, they have 25-year warranties, or sometimes it's a 20-year warranty, but it's a long term. The inverter itself may only have a 10-year warranty at the residential level. At the large commercial or utility scale, it may cost a lot less, but it also will only have a 5-year warranty. Generally, you're doing servicing on inverters. You're swapping out components that have failed. You're not swapping out the entire inverter. And so you look at say a 10-year warranty on the string inverter and a 25-year warranty on the microinverter, and you might conclude that the microinverter is something along the lines of 2.5 times more reliable than a string inverter. The problem is, if your microinverter is 2.5 times more reliable than your string inverter, but you have, you know, 40 of them on the rooftop, you're actually more likely to have a maintenance event on a microinverter system than you would on a string inverter system. You know, the parts individually are more reliable, but there's 40 times as many of them. And so the likelihood, the probability of having a maintenance event is larger with a microinverter system than it is with a string inverter system. You know, when the string inverter system fails, the whole system goes offline, and that's never good. When a microinverter fails, the rest of the system remains online. But you get this problem like 120 solar modules on their rooftop, and there's 2 microinverters that are offline right now that need to be swapped out. The problem is this microinverter is a $90 part. But to get up on that rooftop, I have to get up on the roof and start taking the array apart, swap out the microinverters, re-register them with the monitoring system. That is something that takes 6 or 7 man hours to do. And so you might be spending $500 to replace a $90 part. The economics just don't make sense. It makes a lot more sense to wait until more microinverters fail to service the array. And while that might sound, you can sell that in a way that it sounds good, because it's like, oh yeah, hey, 2 out of 122, you've lost 1.5% of your production. And I gave them a conservative estimate, and so based on the estimate I gave and the production of the array, they're producing more energy than I told them they would produce. On the other hand, I've never met a customer that pulls up their monitoring system and sees one module out of the whole group not working and it not bug them. Almost by recommending microinverters, you're inviting either an unhappy installer or an unhappy customer down the road when you start getting into the maintenance phase of ownership. Now, you still need rapid shutdown compliance, and you still need shade optimization. And so it really comes down to the DC optimizer system or the string inverter system for mainstream solar installers. I wholeheartedly recommend microinverters for new to solar contractors, for do-it-yourselfers. I've done, probably by system count, more microinverter systems than any other. Simply, I work with a lot of new to solar contractors, and it's a very easy starting point. But most solar installers, when they're in the market for a while, they swap over to the DC optimizers because of economies of scale. And then if you're bored in your solar design and you want to take it up to the next level in terms of cost effectiveness, the string inverter, the rapid shutdown combiner, is the most cost-effective combination for an unshaded rooftop. But the reason why I like them is not because of that. The cost differences are fairly close. But what I love about the string inverters with rapid shutdown combiners is I can put this rapid shutdown combiner at the corner of the array, and then all the parts that need to be serviced on the rooftop are at the edges of the array. The module-to-module connections rarely fail. It's more the field-made, field-installed transition points, like where you go from the array wiring to the home run circuit. Those are your failure points. And so, yeah, I like the string inverter rapid shutdown combiner design because it's fewer failure points on the rooftop, and it's the least capital cost. And keep in mind that with string inverters now, they can do track the circuits independently, so you get some shade mitigation. And then finally, you have more flexibility with retrofitting your batteries down the road than you do with microinverters or DC optimizers. Any system out there you can retrofit with batteries. It's just a matter of communication elegance. And then back on that 3 feet off the sides, 3 feet off the top rule, a lot of installers will say, well, my jurisdiction doesn't check for it, or my jurisdiction doesn't require it. And so you get into this point where an installer who's playing by the book stays 3 feet off the sides, 3 feet off the top, and then maybe another installer, presses the design a little bit and goes all the way to the edge. Well, going all the way to the edge may look better. And I'm not trying to say there aren't reasons to go all the way to the edge. There are, aesthetics being one of them. So if your jurisdiction allows it, if you're using a forced ventilation smoke system in your building, you can receive permission from the AHJ to go all the way to the edge, even if their code says you can't. You have to do proper field labeling, to let the fire department know what's going on. But you know, I'm not trying to say that under no circumstance can you go to the edge of the rooftop. You can. But often at the residential level, structural engineering is not required on the system. So many residential projects do not go through a structural engineering process. And what most solar installers do not understand is that the edges of the roof, and particularly the corners of the rooftop, experience higher wind loading than the interior of the rooftop. So if you stick to the interior of the roof, not only is the array much more accessible, not only are you better able by being a little bit, you know, having this extra real estate, you know, that means that if you missed something in your site evaluation, you do have a little bit of wiggle room to play around with. But on top of that, it's better for the structure of the roof itself to stay within the interior of the roof. So there's structural reasons, and if you go all the way to the edge, you definitely are going to want a structural engineering stamp on that to say that you should. To kind of catch us back up on our terminology, we have our solar cell that's put onto our solar module, which is also called a solar panel, but the technically correct way is to refer to it as a module, because a panel is already an electrical term, like your electric service panel. You don't want to confuse the solar panel on the roof with the electric panel that the solar array is tied into. So we have our solar module, and then on the rooftop you have a solar array, and the array may be comprised of multiple strings. You know, it's important to have good aesthetics. I like doing internal conduit runs. I also like accessibility when it comes to, you know, there's a gray area in electric code. You know, electric code says you can mount your pass-through box underneath the solar array, but it says it also has to be accessible. And I don't understand if you go all the way, you know, if you cover the entire rooftop with solar, how anything on that rooftop has an accessible working area. You know, obviously that's not the only thing driving the design, but it is something to think about. So back on this string sizing process, here's our half moon rooftop, and here's our array layout, doing a landscape array in this example. And what we have are 6 circuits of modules, and we're employing kind of the snakes in a basket approach to this design, where actually let me make it even a little more colorful. So that's circuit 1, and then changing our pin color here. Here's circuit 2, changing our pin color again. You know, here's circuit 3, and this is what I would call, and maybe the connectors would reach from going from here to here. You know, maybe instead we'd take this circuit and go from here to there and then back up, because your cable links are fixed. And what we're trying to avoid in the snakes in a basket approach, we're trying to avoid as many field-made splices as we can. I mean, you can build a jumper cable to connect module A to module B, but you know, not only do you get voltage drop the longer your circuits are, but every splice point is a potential failure point. So we'd have to look at this and figure out how to make this connection, but you know, you get the general gist of snakes in a basket. It's just kind of how compact can you make the fewest number of circuits on the rooftop. And so here's all our circuits, but the question is, well, how did I know that? How did I know how many modules would go on each circuit? For that matter, how do I know how many DC optimizers I need or microinverters I need? The answer is you go to the inverter website and you look up their string sizing software. How do we determine how many modules are going to go on which circuit? The answer is you use sizing software that's provided by your inverter manufacturer. So this has to do with wiring modules up to the inverter. The inverter manufacturer wants to make it as easy as possible for you to design a system using their products. So what you're going to do is you're going to select the actual module that you want to design the actual array with. So in this example, we're actually using kind of a non-traditional thin film module, which normally I don't do, but you know, variety is the spice of life. So we're picking out our thin film module. We're entering how many of these modules we're using. We're putting in our array location, and maybe that's not on this specific screen, but you put in your array location, which will give you wind speeds and snow loads. We're putting in the tilt angle and orientation of the array. And the software will check the voltage and amperage at various design requirements and make a recommendation. And it's not going to recommend the best configuration. It's not going to recommend the most cost-effective configuration. It's going to recommend the allowable configurations under the product warranty. So with this thin film oddball solar module, it's telling us which power optimizer to use. And it's saying you can either do one per module, or you can do one for every 2 modules. Telling us, okay, your solar array is 20 kilowatts, and out of our product line, you know, we recommend you doing 2 10 kilowatt inverters. It's going to be on 3 strings each, and so we have 2 total inverters of 6 circuits each, and 1 optimizer for every 2 modules. And so that tells us, okay, we have 2 inverters, 6 circuits, and then we do the snakes in a basket approach to assign the modules to the circuits. You know, if we're just using a regular string inverter without optimizers, it's the same process. You select your module, you select your inverter, you put in your site conditions, which is mainly temperature data. You know, you use the coldest record low because cold temperatures drive up voltage. You're not allowed to exceed 600 volts. So they're checking the maximum system voltage. They're checking the amperage on hot days, but amperage is not as affected by temperature as voltage is. And then you get the different module configurations. So with this 220 watt module on this 6 kilowatt inverter, we could do 1 circuit of 11, 1 circuit of 12, 1 circuit of 13 or 14, 2 circuits of 11, so on, or 3 circuits of 11. So we could have a 33 module system, or a 28 module system, or a 26 module system. But if you look closely, there's no 29 module option or 27 module option. You know, often the circuits on string inverters, they need to be more uniform than the circuits on microinverters or DC optimizers, where you have module level voltage correction going on. But now what you should be able to do is pick out a module, lay it out across the rooftop, be able to go to a racking company's website and replicate that model in the racking software to develop your racking balance of system material. And you pick out your inverter and go and use the inverter sizing software. Now with microinverters, it's a little bit different. You know, with microinverters, you're not doing multiple circuits per microinverter, so the design process is easier. Let's pull open the microinverter spec sheet. And we see from the inverter manufacturer website, I'm also going to pull up a wiring diagram. So like here's a microinverter spec sheet. These are the ones that go behind every module. It's a very plug and play system. We scroll down and we see for a 240 volt system with this particular microinverter, per 20 amp branch circuit, we can have up to 17 modules. Now, the technical reason behind this is the output current is 0.9 amps. And 0.9 amps times 17 will give you about 15.6 amps. And in electrical design, you take that AC amperage, give it a 25% additional allowance for your conductor sizing, and that gives you 15.6 amps times 125%. It's about 19 amps. You round up to the nearest breaker size, and lo and behold, it's on a 20 amp branch circuit. So 17 is the maximum number of microinverters you can place on this circuit and not trip the 20 amp breaker. So the design's already done for you with microinverters. It's just, is the module compatible with the microinverter, and then how many modules you have. You get wiring diagrams that will explain to an electrician, exactly what's going on with the circuit. You can also get installation manuals, and this is for inverters and racking systems too. And it just, let's scroll through the text, but it gets into, lightning protection and tools and equipment lists and the exact, kind of installation methodology. So there are construction documentation. It's just generic. It's not specific to your particular job site. So through the combination of good construction manuals and clearly defined work scope, I don't think it's too much to expect an electrician to be able to look at this wiring diagram and understand what's going on. Just because they don't have any solar experience doesn't mean they shouldn't be able to read this wiring diagram. So you should be able to model your array layout in a racking system and then come up with the racking bill of material and model the inverter layout in the stream sizing software and know how many inverters you're using, and also from your layout how many modules. So what we're able to just very quickly determine in solar design is the racking bill of material, the inverter bill of material, and the module bill of material. And actually, one nice thing about micros is after you buy all these parts, that's pretty much it in terms of specialty solar parts that you need to do a job. There might be some specialty parts that make your job easier, but you could literally buy this stuff from the solar supplier and put the rest of the system together based off of off-the-shelf parts at Lowe's or Home Depot or Menards or whatever part of the country you're in, your local supply store. When you're developing this rooftop sketch, trigonometry can be employed, and here's a good reason. This is a tool that's commonly used for getting up on the rooftop and determining where shadows are going to fall exactly where you stand. And so you have it's called the Solar Pathfinder, and the axis along the x-axis you have hours of the day, and along the y-axis you have months of the year. So you get up on the roof and you sketch out where nearby objects kind of fall along this dome. The takeaway here is this solar array where this guy is standing, in the summertime, an array could be on from 7:30 to 6, and what we see is the sun is going to come right up over this tree line in June and July, right around 7:45. So we're not going to, or 8 o'clock when you get into May and July. And so this solar array, we're going to lose maybe a half an hour in the morning for right where he's standing. That's no big deal. And then, even though this house is a bit more of a concern, actually in the winter time, the days are shorter. So having a solar window in the winter from, it might be from 9 to 3, and we lose a little bit at that time. But, this is a good solar service. You're really looking for, about 8 hours of sunlight in the summertime and about 6 hours of sunlight in the wintertime, uninterrupted. But the thing you have to keep in mind is even if you're doing the most exact on-site analysis, trees grow over time. And so over time, unless you trim that tree, that part of the array is going to become shaded. There's actually a law called a solar easement, where if your neighbor shades your solar array, you can take them to court for lost compensation. We'll talk about that in a little bit. Instead of doing an on-site evaluation, and we know that on-site evaluations, the most accurate ones, still do not reflect things like tree growth. So actually, computer modeling of solar job sites can be very similar to the most robust site evaluations. Now, this is a commercial solar software called Aurora. And what's neat about Aurora is they have a really great visual integration of what's called LiDAR data. This is the same technology that autonomous or self-driving vehicles use to map out the terrain. Well, you can put these cameras on a airplane or a helicopter or a drone and collect topographical data. And it's so exact, it'll tell you things like tree height and roof slope and chimney height. And what we've done here is modeled our trees, but then we've grown our trees a little bit to more finely tune the reasonable expectation of what the solar array will do over the first few years of its life at the very least. So, you know, once you get into working regularly in the solar industry, if you're not just trying to do a one-off project, you know, getting into solar design software really helps you move things along. You know, so Helioscope is a competitor to Aurora. Their LiDAR data isn't as good. Their 3D modeling is not as good, but sometimes a less feature-rich application can actually be more pragmatic in your workflow. What's nice about Helioscope is it's really great for rapid modeling. And so in the past, you might have gone to site and performed an extremely rigorous site evaluation, even as part of the bid process before the client is really locked in. I don't think that that's particularly wise. I think it's better to sell the client a design package and then get the project ready for construction, and then, you know, either they can go to construction with you or somebody else, but you're not putting a lot of overhead into a design process that might not even come out of the ground. There's not a lot of customers doing design services in the solar industry right now. But with rapid modeling, you know, instead of just giving your customer one design, you could say, okay, well, you know, normally the solar installer will be out there and they're going to avoid the tree, and they say, okay, we're going to do a small solar array that avoids the tree, but you're going to have a little bit of shading. But now I can say, okay, this is the size of the array if you keep the tree. This is the size of the array if you, this is the production of the array if you chop the tree down. So now they can put a dollar and cents value on tree removal, or tree trimming for that matter. In addition to that, not just doing the south side of the roof, but doing the entire roof. You know, if we do the south side, it's this size. If we do the entire roof, it's that size. If you keep the tree, it's this much production. If you chop the tree down, it's that much production. And you let the client choose. And you can even model different weather conditions from different local weather monitoring stations to get a range of production, which can vary a little bit based on what weather station you use to generate your data set. And so rapid modeling allows you to get through the bid process much more transparently, but in a professional manner, and gives the client more flexible options. And so we teach a Design Your Solar Roof class that goes more into depth into these functions, but you can model commercial demand and battery management. Solar design tool will give you national electric code reporting, also makes a stab at bill of material lists, and has a really great one-line electrical diagram drawer. Often on a residential project that doesn't have any shade, Solar Design Tool is no good for shade analysis. But I'll run a design through Solar Design Tool so that when I drop off my permit, I can print out and include a National Electric Code compliance report that looks really professional. An inspector, even if they haven't heard of me before, even if they might be unsure on what solar is, particularly in a developing market, stuff like this makes the inspection process go along a lot more confidently. And I remember when I got into the solar industry, the one-line diagrams that we would give the utility would be done on like Microsoft Paint. Now, this document you see in front of you that has multiple branch circuits of microinverters with various technical data, this document is 100% automated, where I did not hand draw or model in CAD or anything like that. Anything that you see before you, this is a 100% computer generated document. We're getting to that point in the solar industry, just like in other professional building design industries, where the capabilities and accuracy of the industry software is improvement upon the pencil and paper process, where it used to be you'd be kind of hands-off on solar design software because you couldn't be confident in it. Now most of this software has been on the market for over 5 years.